Hello viewers, this is U.A.C.E taking you through advanced level chemistry. So in this video we are going to be looking at inorganic chemistry. We are going to be undertaking the topic of periodicity best for senior 5 and senior 6. So my name is U.A.C.E and if you are doing advanced level chemistry, inorganic chemistry is one of the simplest but trickiest branches in advanced level. So if you're watching this video, I advise you to pick your notebook or summary book and follow my explanations. So as we are starting, periodicity is divided into the following subtopics, and we are going to be explaining each one individually. I've told you pick your summary book, or if you don't have notes, you can first pause the video and note down the notes before I start explaining them. So in this video, I'm going to explain how each of the following is formed, right from atomic radius to standard electrode potential. But standard electrode potential will be reviewed more in physical chemistry. So in this video, I think it was excluded. So we are going to be looking at atomic radius, ionization energy, electron affinity, electronegativity, electropositivity, metallic character, standard electrode potential. Now notice that all of these variables have the same structure of explanation. That's what makes it easy. So I'm going to give the structure of explanation in the next slide, but you must know that they have the same factors that we look at while we are marking them. So pay attention as we proceed to the next slide. Now, factors affecting atomic properties of elements include nuclear charge, denoted by Z, screening effect, denoted by S, electronic configuration, and atomic radius. So these are the factors that you are going to be looking for when you are marking the way you are going to approach chemistry explanations, especially for periodicity. Now, periodicity is everywhere in inorganic chemistry. Every topic you begin with periodicity, so it's very vital to understand each of the following and how each of them is explained, especially these first two, the nuclear charge and screening effect. Electronic configuration must also be understood properly. So make sure that if you don't have these notes, you pause the video, you first note down the notes before I start my explanations. So the order of answering periodicity questions is as follows. Number 1, we talk about the effect of nuclear charge and what causes it. Like if you're talking about increase in nuclear charge, what will cause the increase in nuclear charge? So you find that nuclear charge will increase due to additional or increase in the number of protons in the nucleus of the atom or the ion, depending on what you are explaining. If you look at screening effect, the effect of screening effect first of all remains almost constant if you are adding electrons to the same sub-energy level. But screening effect only increases if you are adding completely filled energy level of electrons. Let me sketch that one here so that we can understand how screening effect is brought about. So if you're having an atom, let's say that this is the nucleus N of the atom, and this is the one of the sub-energy levels, and you're having electrons here, electrons here, electrons here, and electrons here. So, and we get another sub-energy level on top of this. So we also have electrons here, electrons here, electrons here, electrons here. So what we mean by screening effect is the repulsion caused by these electrons in this inner sub-energy level onto the electrons on the outermost sub-energy level. So the force that comes from the electrons in this inner sub-energy level onto the outermost sub-energy level is what we call the screening effect. So screening effect will be increasing if completely filled energy level of electrons are going to be added, but not that screening effect is going to remain constant if at all the electrons are being added to the same energy level. This is not going to remain constant, but it remains almost constant. And in that case, we shall look at across the period. So across the period, you'll find that electrons are being added to the same energy level. So we expect screening effect to remain almost constant. If you look at across the period we shall be having additional completely filled energy level of electrons. So we expect screening effect to be increasing down the group. This is because we are adding completely filled energy level of electrons. So when you're explaining that, we need to see that reason well stated, that screening effect is only increases when completely filled energy level of electrons are being added to the atom. And screening effect remains almost constant if at all electrons are being added to the same energy level, like I've just illustrated. So the third point, we look at the effective nuclear charge. So across the period, since screening effect will remain almost constant and effective nuclear charge will be increasing due to increase in the number of protons, we expect that effective nuclear charge will increase. This is because effective nuclear charge is the net positive charge on the atom of an element. So we expect effective nuclear charge to be increasing with increase in nuclear charge, and with this screening effect remaining almost constant, and that will be only across the period. So across the period, we expect effective nuclear charge to be increasing. Then what about down the group? So we have looked at down the group, and we have said down the group, effective screening effect is going to be increasing, and it's increasing because you're adding completely filled sub-energy level of electrons. So once screening effect increases, its effect is going to its increase is going to outweigh the increase in nuclear charge. And once screening effect increases more than nuclear charge, that means that the effective nuclear charge is going to decrease. Now, effective nuclear charge exerts its effect only on the outermost electrons. So since if effective nuclear charge is higher, we expect the outermost electrons to be more strongly attracted to the nucleus. And if effective nuclear charge is low or decreases, we expect the outermost electrons to be less attracted towards the nucleus of the atom. And when the outermost electrons are strongly attracted towards the nucleus of the atom, we expect a decrease in atomic radius. Since electrons present in the outermost energy level, if effective nuclear charge present here is greater, it's going to attract these outermost electrons towards the nucleus. So we shall see a decrease in atomic radius. And if effective nuclear charge is low, these electrons are going to be less attracted to the nucleus. So we shall have an increasing tendency in atomic radius. So going on to the next point, we look at the conclusion. Now here the conclusion is the factor you are explaining. Like for example, there are a lot of, we have looked at atomic radius, ionization energy, and electron affinity. Now the others, the explanation remains the same. You explain things the same way. All these will remain the same on each and every factor of periodicity. But the conclusion is what's going to vary, depending on whether you are explaining ionization energy, atomic radius, electron affinity, standard electric potential, among others. But note that we need these marking points in your explanations. So let's hop on to the next slide and we see how we can include that in our explanations. Now let's begin by finding out what each of the followings mean. We have looked at nuclear charge. Like as I said, if you don't have the notes already written down, you first pause the video at each and every slide, you write down the notes. After doing that, you play the video for my explanations. So if you're looking at nuclear charge, we have said this is simply the total number of positive charges in the nucleus of an atom. It is equivalent to the number of protons, implying that nuclear charge is the net positive charge in the nucleus of the atom. The higher the number of protons in the nucleus of an atom, the higher the nuclear charge. Let me hope that's simple to understand. Like as I explained screening effect. Now I've just previously explained screening effect using a sketch in the previous slide. And you're seeing that this is the repulsion of the outermost electrons by those in the innermost sub-energy levels from nuclear attraction. And you have said that the greater the number of energy levels, the greater the shielding or screening effect. So you find that across the period, electrons are being added to the same energy level, so we don't expect any significant increase in screening or shielding effect. But across the group, we are adding completely filled energy level of electrons from one element to the next. So we are expecting screening effect to be increasing down the group. If you look at the effective nuclear charge comes after explaining nuclear charge and screening effect. And what outweighs the other is what brings up the conclusion of this. If nuclear charge increases more than screening effect, we expect an increase in effective nuclear charge. But if shielding effect increases more than nuclear charge, we expect a decrease in effective nuclear charge. Effective nuclear charge refers to the net positive charge on the nucleus of an atom or ion experienced by an electron. And we say that the impact of effective nuclear charge is exerted on the outermost electrons. If outermost electrons are strongly attracted to the nucleus, we shall experience a decrease in atomic radius. And if effective nuclear charges experiences a decrease, the outermost electrons are going to be less attracted to the nucleus. So the atomic radius of the atom will be having an increment. So let's start with the first periodic term, which is the atomic radius. Atomic radius refers to the half the distance between the nuclei of two adjacent atoms provided bonded in a gas or metal. Now there are lots of definitions for atomic radius, but what we want to see that it's the half the distance between two nuclei. Some textbooks say half the internuclear distance, for as long as it's half. And the other key item that must be in your definition must be covalently bonded atoms. The atoms must be covalently bonded. Now let's look at the factors that determine the size of an atom, or what we can present as atomic radius. Now as I told you in the previous slide, I told you that factors are always the same. We shall look at nuclear charge, we shall look at spin effect, and after looking at both of those ones, you have to state the effect on the effective nuclear charge. So that's the order of explanation of each and every periodicity term, like as you are going to see in the subsequent slides. So as usual, I told you, you first pause the video, you take the notes, and then you resume later. So we are going to start with nuclear charge. And you're saying that nuclear charge is determined by the number of protons which exist in the nucleus of an atom. That means that the higher the number of protons, the higher the nuclear charge. And spin effect always depends on number of energy levels. That means that the lower the energy levels, the lower the spinning effect, like I've already explained in the previous slides. And the higher the number of energy levels, the higher the screening effect. Now, after explaining both of those ones, you have to talk about the effective nuclear charge. As you are seeing the definition, that this is the resultant force that occurs after comparing the trend variation in both the screening effect and nuclear charge, implying that you cannot talk about effective nuclear charge before talking about screening effect and nuclear charge, either across the period or down the group. Now we are saying that if the increase in nuclear charge outweighs the increase in screening effect, like I already said earlier, effective nuclear charge is going to increase, because effective nuclear charge is the resultant positive charge on the nucleus in the atom. So if nuclear charge increases, or if the number of protons increases, we expect more than the spin effect, we expect an overall increase in effective nuclear charge, and its opposite to spin effect increasing. That's why you're saying that, however, if increase in screening effect outweighs increase in nuclear charge, there is a decrease in effective nuclear charge, because screening effect is concerned with electrons which are negative, and effective nuclear charge is concerned with positives. So if the increase in the negativity is greater, we expect the positive to lower. That's why we are saying that if screening effect increases and outweighs increase in nuclear charge, there will be a progressive decrease in effective nuclear charge. Now note that some students always misinterpret this explanation. When they reach here, they say that the screening effect outweighs the nuclear charge. That's not the case. Here, note that it's the increase in screening effect. Let me highlight this one using red. Increase in screening effect is the one which outweighs the increase. It's not that screening effect outweighs nuclear charge, it's the increase. Both of them are increasing, but the increase of the other outweighs the other. And after stating that, we state the effect on the effective nuclear charge. So you find that here effective nuclear charge is going to be decreasing. Are you together? So what would happen if, like here we said earlier, increase. We are talking about increase. We are not talking about nuclear charge individual. It's the increase. Increase in nuclear charge outweighs the increase in screening effect. And if that happens, you'll find a progressive increase in effective nuclear charge. So here we are having a continuation, and it's saying that increase in effective nuclear charge results into the outer electrons to become attracted more strongly to the nucleus, and vice versa. As I told you earlier in the previous slide, is that if effective nuclear charge increases, the outermost electrons are going to experience stronger nuclear attraction, and if they experience stronger nuclear attraction, that means that we shall have a decrease in atomic radius. And if the effective nuclear charge decreases, outermost electrons are going to experience low nuclear attraction. That means that we shall have an increase in atomic radius. Now let's start looking at trend variation. Variation of atomic radius across the periods. Like for example, you can state any period. I think period 3 is right. Now note that when you're handling periodicity, always make sure that if you're having a periodic table at your school, you are having it as you are reading your periodicity, because everything is given. You have the values of atomic radius, electronegativity, standard electrode potential, and ionization energy given, and you are given a key to see them. The key you are given is always on your left hand side at the top using copper. So learn how to interpret the periodic table and learn how to use it. So let's start, and as I've already said, if you don't have the notes, you first pause the video, you take the notes, and then you play the video for my explanations. So do that quickly. So let's look at across the periods. For example, any period like period 3. So you find that such questions are always asking you for two things. In the question bank, if you open the question banks, we shall always ask you state the trend and then explain. And I brought my notes in that form. First of all, I first state the trend and then I go to explanations, and that's the same way you are supposed to present your answers. So if you look at trend of atomic radius across the period, trend of atomic radius across the period. So I shall say that generally atomic radius decreases from left to right across the period of the periodic table, and that's to say from one element to another. Like I've told you, an example of period you can look at could be period 3. So we expect atomic radius to be decreasing from sodium to argon. And what could be the explanations? Like I've told you, the explanations for periodicity are going to be in the same way. First of all, you'll be talking about nuclear charge, as I stated it here. Secondly, you'll be talking about spinning effect, as it's present here. And then thirdly, you'll be comparing the two, and then you talk about effective nuclear charge, as I mentioned it here. And then lastly, we talked about conclusion, and your conclusion will be this one. So you find that all these items are divided, and each of these statements is going to carry 1 mark. 1 mark. Effect on nuclear charge, and what will the nuclear charge have the effect on? So you find that such questions will total to around 0.4 marks, and if it exceeds that, then the 1 mark will be for stating the trend. This one will carry 0.1 mark. So let's start explanation. Across the period, as you move from one element to the next, a proton is being added to the nucleus of the atoms. That's from one element to another. And as you're adding protons, that means that you're leading to an increase in nuclear charge. Like as I told you earlier on, nuclear charge is equal to the positive charge on the nucleus of an atom, and protons are positive. So as you're adding proton across the period, you are increasing the positive charges in the nucleus of the atom, hence increasing the nuclear charge. That's why it's being summarized as a proton is being added from the to the nucleus of an atom from one element to another, there will be an increase in nuclear charge. And here we are saying at the same time, electrons are being added to the same energy level and therefore increasing. Like I told you, across the period we shall be adding electrons to the same energy level and therefore increasing the screening effect by electrons only slightly. When you're adding electrons on the same energy level, screening effect does not increase. It only increases slightly because so we say that screening effect can only increase when you're adding completely filled energy level of electrons. Let me hope you got that clear. And then we say that, however, increasing nuclear charge outweighs increasing screening effect of the electrons. Like as I told you earlier on, after explaining nuclear charge and screening effect, you have to state the effect, which one won the other. So the one which won the battle will have the effect on nuclear charge. So you'll find that since screening effect is remaining almost constant and nuclear charge is increasing nuclear charge will outweigh increasing screening effect. And that's why we are saying, however, increasing nuclear charge outweighs increasing screening effect of the electrons, which results into an increasing effective nuclear charge. Now try to pause the video and remember, what did I talk about effective nuclear charge? Which impact does it exert on the others? So let's look at the conclusion. That's what effective nuclear charge. What do effective nuclear charge have? We say that effective nuclear charge will only have effect on outermost electrons. And if it increases, outermost electrons are going to be more strongly attracted. But if it decreases, outermost electrons are going to be less strongly attracted. And if they are more strongly attracted, we shall experience a decrease in atomic radius. But if they are more strongly attracted, if they are less strongly attracted, we shall experience an increase in atomic radius. That's why we are saying, therefore, the outermost electrons become strongly attracted to the nucleus, leading to a decrease in atomic radius of elements across the period. So let's proceed with ionization energy. Now, ionization energy, I want you to pay attention to this one because it's commonly said. Ionization energy, I want you to simply understand that it's just the removal of electrons, and it's always energy required because to remove something you require energy. So removal of electrons from an atom or an ion is called ionization energy. I want you to remember that whenever you are removing something, you require energy. And when you are adding something, you evolve energy. So that's the key to this, to master this concept. Ionization energy is given two definitions, and one is singular and the other is in plural. Don't mix the two. When you are going to use the definition containing one more, make sure that everything is in plural. The A's, this must be electrons. Whenever you're using one more, this must be atoms. You make sure that everything is in plural. That's where most students fail from, because their teachers didn't emphasize about it. So if you are done with the notes, you go back, look through your notes, look through your definition, and rectify it. So in plural, ionization energy can be defined as energy required to remove completely 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. Everywhere you're using more, make sure that everything is in plural. You're using more, make sure that everything is in plural. You're using more, everything is in plural. Most students have a habit of combining the two. He says that the 1 mole of electron and it goes to 1 mole of gaseous atoms and it goes to 1 mole of gaseous ions. That's not true. Everything must be pure because this is what we look at. Or simply one can define it in terms of singular. Like we said, ionization energy can be defined as the energy required to remove an electron. Now here you are explaining it in terms of singular, that's why you're using an electron from the valence shell of an isolated gaseous atom to form a gaseous ion, as simple as that. So simply, energy required to remove an electron from a gaseous atom to form a gaseous ion can also be referred to as ionization energy. But when defining this term, be cautious about your tenses you are using. If you are using mole, make sure that everything is in plural: electrons, atoms, and ions. If you're not going to use more in your definition, make sure that everything is singular. Energy required to remove an electron, 1. Form a gaseous atom, still 1. To form a gaseous ion. And I've told you it's always energy required, it's not enthalpy change. If you're having enthalpy change in your notes, try to go and rectify it. To take out an electron from an atom, we always require energy, so this is key. When you're marking, you shall put half a mark, but a student who has said energy change may be denied. Because to remove something from an atom, we need energy. So let's look at first ionization energy. Like as I told you, ionization energy is always energy required. And for every electron that you remove, we require energy. Now, first ionization energy simply, in simple terms, refers to the removal of the first electron. And second ionization energy refers to the removal of the second electron. Similar applies to the third ionization energy, which will be the removal of the third electron. So, how are we going to define first ionization energy? The only difference from the normal definition of ionization energy is the product that's being formed with the first ionization energy. First of all, you have to recognize that it's always the minimum amount of energy required, or you can just simply say amount of energy required. So I opted to define it in terms of moles, but someone else can define it in terms of the singular. And I said, if you're using moles, you make sure that everything is plural: electrons, atoms, and ions. So take note of that. So first ionization energy refers to the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, forming 1 mole of positively charged gaseous ions. Now note that the only difference starts from here. We form 1 mole of uni. Uni means 1. So that's about first ionization energy. We are removing 1 electron. So once we remove 1 electron, we form uni positively. So here we define it in terms of moles. So we are removing 1 mole. Once you remove 1 mole, you shall form uni positively. 1 mole of positively charged gaseous ions. And I've already told you, when you're defining in terms of moles, make sure that everything is in plural. Don't miss out on these ones. You are going to lose marks. So this equation, I think it was improperly typed, but you can type it as you're writing your work. Like as I already mentioned earlier, if you don't have these notes, you first pause the video and make sure that you take down some notes for this slide before I explain them. So this equation was not written properly, but you can visit a textbook. Magnesium in gaseous state will give you, after losing 1 electron, after giving off 1 electron, removing 1 electron, to give you magnesium ion. And each and every coefficient is 1, 1. That means that you're forming uni. first ionization energy is about uni or 1. The second alternative definition is the one which is in terms of singular. And we are saying that first ionization energy is the amount of energy required to remove an electron from a gaseous atom, forming a positively charged gaseous ion. So notice that this one in singular, we don't use gaseous ions, we use gaseous ion, and we don't use gaseous atoms, we use gaseous atom, and we don't use electrons, we use electron. So there are two. When you're using moles, always remember that everything must be plural. When you're using singular, always remember that everything must be singular. So let's look at the second ionization energy. Now, these things are progressive, implying that after the first ionization energy, we go to the second, but it's still going to be energy required, because to remove an electron, we always require energy. So it was defined in terms of moles. That means that each and every word you're going to use must be plural. And we are saying that energy required to remove 1 mole of electrons from 1 mole of univalently charged gaseous ions to form 1 mole of divalently charged gaseous ions. So take note of that. This was tried to be organized. But when you're writing these equations, because they're always examined, make sure that you are writing everything in gases, because in your definition you told us we are dealing with gaseous ions, gaseous atoms, and then make sure that your states are in gases. Most students put them in solids. So is the energy required to remove 1 mole of electrons from 1 mole of univalently charged gaseous ions? We are saying univalently charged gaseous ions because first ionization energy is one that first takes place, and first ionization energy gave us univalent or positively charged gaseous ions. So removal of electrons from these positively charged gaseous ions will take us to dipositively or divalently charged gaseous ions. So we start from here, we pick this, and here we remove my electron from it so that we can remain with Mg2 plus. Let me hope that has been clear. For anything that seems unclear, always rewind the video and try to pay attention. Now let's look at the other item, which are the factors affecting the magnitude of ionization energy. And these factors are going to remain the same, like we started with earlier on. We shall look at nuclear charge, spin effect, atomic radius, and also electronic configuration. Now, since ionization energy is the energy required to remove an electron from the atom, what do you think will be the factors affecting that removal? If you are to look at nuclear charge, if nuclear charge is greater, outermost effective nuclear charge will be high. Outermost electrons are going to be strongly attracted to the nucleus. That means that removal of an electron will require a high amount of energy. And since high amount of energy is required, that means that ionization energy correspondingly will be high. If you look at atomic radius, the smaller the atomic radius, the more strongly the outermost electrons are attracted to the nucleus. That means that removal of an electron for such an atom will require a very high, significant amount of energy. So in this explanation, we are saying that the bigger the atomic radius, the lower the ionization energy, and the smaller the atomic radius, the higher the ionization energy. Like as I've already explained, if the atomic radius is smaller, these outermost electrons are going to experience stronger nuclear attraction from the nucleus as they are nearing it. But if the radius is bigger with numerous energy levels, the outermost electrons are going to experience low nuclear attraction. That means that they are going to be less attracted to the nucleus. So let's hop on to the next slide and look at the explanations. As I've already explained, I'm just going to be going through this essay. As I told you, if you don't have the notes, if you find that to remember my explanations will be safe and easier, you take a book, pause the video and take the notes before you listen to what I'm explaining. So, as I already explained, for atoms with small atomic radius, outermost shell electrons are close and they are going to be strongly attracted by the nucleus. Hence, we expect high amounts of energy to be required to remove the electrons present on those energy levels. Whereas for large atomic radius atoms, outermost shell electrons are going to be far away from the nucleus. That means that they will be experiencing less nuclear attraction. And once the outermost electrons experience less nuclear attraction, energy required to remove them is going to be low, which correspondingly will lead to a lower ionization energy. However, if atomic radius is smaller, we expect the outermost electrons to be closer to the nucleus. That means that the outermost electrons are going to be more strongly attracted. Therefore, to remove an electron from such an atom is going to require high amount of energy, hence high first ionization or ionization energy. Now, looking at other factors, we have the nuclear charge and screening effect. Now, I'm just going to go through these ones since I've already explained them. The greater the nuclear charge provided, the screening effect increases only slightly, and that only happens across the period. I want you to pay attention to this statement. Increases only slightly. Provided the screen effect increases only slightly. The screen effect will only increase slightly if it's across the period, and the reason for that I told you, because we're adding electrons to the same energy level, and screen effect is increasing because we are always adding protons to the nucleus. So you're saying that the greater the nuclear charge provided the screen effect increases only slightly, the higher will be the ionization energy. And you are saying that this is because there will be an increase in effective nuclear attraction for the electrons, and therefore increased amount of heat energy will be required to remove the electrons. However, the lower the nuclear charge, the lower will be the ionization energy, and the reason for that, outermost shell electrons will be less strongly attracted to the nucleus, and once they are less strongly attracted to the nucleus, that means that the amount of energy required to remove an electron from those shells is going to be low, which subsequently leads to a lower ionization energy. Now let's proceed on to the next term or factor. Next factor, we are talking about screening effect. Now you should know when the screening effect, by now you should know when the screening effect is increasing and when it's remaining almost constant. We said screening effect increases as a result of addition of completely filled energy level of electrons, but it remains constant as a result of addition of electrons to the same energy level. So, screening effect we expect it to remain almost constant across the period, but we expect it to increase than the group. That's why we are saying that the lower the screening effect, the higher the ionization energy. And the reason behind that is because outermost electrons are strongly attracted to the nucleus. And once outermost electrons are strongly attracted to the nucleus, that means that higher amounts of energy will be required to remove an electron from such an atom or ion, increasing its ionization energy. So as we are finalizing ionization energy, we are saying that note Now be aware of these notes because the notes are very important. The more the inner energy levels, the greater the shielding or screening effect, thus the lower the ionization energy. And why are we saying so? When screen effect increases, remember screen effect is a repulsion of the outermost electrons by the electrons present in the innermost energy levels. That means that if you are repelling away outermost electrons, energy required to remove them from such an atom will be lower. So the greater the repulsion or the greater the screen effect, the lower the ionization energy. So that was variation across the group. Let's look at variation across the period. Like as I've stated, that questions in this are asked in this manner: state and explain. When you see such a question, it requires two answers. First of all, you start by stating the trend, and secondly, you go to explanations. Now, always remember that if you don't state the trend, there's no way we can mark your explanation. So, what do you think will be the trend across the periodic table? Now, here we are saying that generally the first ionization energy increases from left to right across a period as the atomic number increases. Why do you think first ionization energy is increasing from left to right across the period? Now notice that in this explanation, as I told you that to explain periodicity terms the same way, you are going to look at nuclear charge and what causes it. You are going to look at screen effect and what causes it. And after that, you look at effective nuclear charge. Effective nuclear charge, which is around here. Let me hope that's very clear. So across the period, you find that nuclear charge is increasing. And why is it always increasing? It's due to additional protons to the nucleus. Once we are adding protons to the nucleus, we shall always find an increase in nuclear charge. However, screen effect is going to remain almost constant. And the reason for that is because electrons will be added to the same energy level. But here you must talk about the conclusion before we talk about effective nuclear charge. So you find that the increase, I'm still mentioning this one because many of you make errors from here. You just say that the nuclear charge outweighs the screen effect. No, that's wrong. It's the increase in the nuclear charge that outweighs the increase in screening effect by the electrons in the same energy level. So after talking about which one outweighs the other, you have to talk about effective nuclear charge. Like in this case, increasing nuclear charge outweighs increasing screen effect. That means that we expect an increase in effective nuclear charge. And we see that if effective nuclear charge increases, attraction of outermost electrons will increase. Now, if outermost electrons are strongly attracted by the nucleus, that means that to remove such an electron will require significantly higher amounts of energy, which correspondingly leads to higher values of ionization energy. So in proceeding, we shall have a look at exceptions. Now, for the case of exceptions, the ionization energy of helium is higher than that of boron. Now, for exceptions, in most cases, they compare to elements. And whenever they are comparing two elements, you are supposed to first state their electronic configurations. Exceptions in chemistry of elements among periodicity, like the explanation lies in their electronic configurations. You'll find that some elements will have a completely filled outermost energy level, whereas others are going to have a halfly filled energy level. And we are going to say that such elements are going to be thermodynamically stable. And with such elements, to add an electron or to remove an electron, or whichever periodicity concept you are explaining, since it's thermodynamically stable, energy will be required. More energy will be required. Or if you are dealing with electron affinity, there will be less energy being released because such elements are thermodynamically stable. So we are saying that for barium and boron, ionization energy in barium is higher than that of boron. And why is that the case? We are saying that this is because barium atom has a completely filled to a sub-energy level with 2 electrons. Now if you look at the electron configuration of barium is this one. For the S sub-energy level to be fully filled, it requires 2 electrons. That means that barium has a completely filled 2s energy level. Whereas in boron has the configuration of this. That means that boron is having only 1 electron in the 2p sub-energy level. Now note that this is not, we don't call this partially filled. Partially filled means that can also mean halfly filled. So any students have a tendency of writing partially filled. Partially filled is wrong. You state the number of electrons present and you tell us that it will be thermodynamically unstable. So if you look at boron, it only has 1 electron in the 2p sub-energy level, whereby this one will become thermodynamically unstable. And once an element is thermodynamically stable, to add an electron, to remove an electron will require less energy. But for boron, since it has a free field to a sub-energy level, to add an electron will require, to remove an electron will require more energy. Hence, we expect ionization energy in barium to be higher than that of boron. So proceeding, we are having the stable orbital. We are saying that the stable orbital will require more energy for an electron to be removed compared to one which is unstable. Thus, higher ionization energy of barium compared to that of boron. Now, I want to note that other explanations are going to remain the same. Now, in this case, we are comparing nitrogen and oxygen. Now notice that nitrogen is having a halfly filled 2p sub-energy level. That means that nitrogen atom is thermodynamically stable. Thus, to remove or add an electron is going to require more energy. That's for the case of ionization energy. And for oxygen, it has only 4 electrons. I said this is not partially filled. This is called, you say the number of electrons. If it's neither partially filled or full, if it's neither fully filled or fully filled. So we expect nitrogen to be more dynamically stable. So that means that to remove an electron from nitrogen atom is going to require a significantly higher amount of energy compared to the energy that will be required to remove an electron from the oxygen atom. So the reason all lies in oxygen having only 5 electrons in the 2p sub-energy level, which is neither halfly filled or fully filled. This makes the atom of oxygen thermodynamically unstable. But for these ones that are fully filled or fully filled, their atoms are thermodynamically stable for half-fully filled or fully filled elements. Therefore, since thermodynamically stable, removal of an electron requires significantly higher amount of energy. Now you're saying that partial ionization energy of aluminium is less than that of magnesium. Try to pause the video and do this as an assignment. Try to find out the reason why. For those of you who haven't copied the notes, pause the video, take the notes and proceed to the next slide. And for those of you who have read the notes, try to summarize some of these because your notes may be lacking them. So if you are to look at the reason why magnesium is having a higher ionization energy than aluminium, if you look at the electronic, I said when you're comparing two elements, you write their electronic configurations. If you look at the electronic configuration of magnesium compared to that of aluminium, you'll find that for aluminium, you have neither partially filled or completely filled energy level. So aluminium was missing. I messed up the 3p. I think it's 3p1. 3p1 is missing here. So this was incomplete. There had to be a 3p1 sub-energy level here. That's why we are saying that for magnesium, electron is being removed from the 3s sub-energy level or 3s orbital, which is completely full with 2 electrons. And we say that for completely filled or half-filled sub-energy levels, they are energetically stable, or you can say they are thermodynamically stable. And once an element is thermodynamically stable, will require significantly more amounts of energy to remove an electron. That's why we are saying that for magnesium it will have a very high ionization energy. What about aluminium? For aluminium, since its electronic configurations end with 3p1, we expect that it's neither halfly filled or partially or fully filled. Therefore, it's going to be thermodynamically unstable. So that's why aluminium is having the 3p orbital with only one electron. I think you can eliminate the use of this orbital to sub-energy level. Where I placed orbital, you can edit channels to sub-energy level with only one electron, which is neither completely full or halfly filled. And if it's neither completely filled or halfly filled, it's energetically stable because it only has one electron. So we shall be marking that, but we shall be denying marks for students who are saying partially filled, because partially filled can mean that an atom is either halfly filled or is neither halfly filled. So partial filled does not apply. If you see that anywhere, your work will be rejected or ignored. Less amount of heat energy will thus be required to remove an electron from aluminium atom compared to that of magnesium atom. Another assignment was, similarly, the first ionization energy of sulfur is less than that of phosphorus. Now, since we are going to be looking at the same concept, I've decided to skip this one. For those of you who do not have the notes, try to pause and try to write down this assignment. Try to answer it on your own. Pause the video and come back and see the solution. So if you look at it, I said if you're comparing two things, you first start by writing their electronic configurations. After writing the electronic configuration, start your explanations. So you see that in phosphorus, we are having a halfly filled 3p sub-energy level, whereas in sulfur, we are having neither a partially or fully filled 3p sub-energy level. So, the phosphorus atom will be thermodynamically stable or energetically stable, depending on the sparing that you manage. Whereas in sulfur, the 3p sub-energy level is neither halfly filled or partially filled. And for those ones that are half-filled or fully filled, since they are thermodynamically stable, to remove an electron requires significantly higher amounts of energy. Whereas for these ones that are neither half-filled or fully filled, they are thermodynamically unstable. Thus, to remove an electron will always require less amounts of energy. So you find that the ionization energy in sulfur is significantly lower than the ionization energy in phosphorus. Now looking at the variation of ionization energy down the group of the periodic table, it said these questions are set in such a way that they first tell you to state the trend, and then they tell you and explain. Those are two separate questions, so you have to start by stating the trend first, and then explanation follows. Most students fall into a trap of just beginning to explain without starting the trend. Know that if you begin to explain without starting the trend, your marks are going to be denied. So you're saying that first ionization energy, for those ones who don't have the notes, first pause the video and write down the notes. After that, you play the video and listen to the explanation. So you're saying on descending the group, there is an increase in nuclear charge. Like I told you, we are going to be repeating the structure of explanation. Nuclear charge, what causes it? Screening effect, what causes it? What outweighs, after explaining the effect of increase in nuclear charge and effect of increase in screening effect. And then you talk about effective nuclear charge, and then you say the conclusion. That's the order of explanation of all periodicity questions. So this looks like a paragraph, but we have already covered all this one. What's going to vary is going to be the conclusion. So on descending down the group, there is an increase in nuclear charge, and the reason for that is due to increase in the number of protons. At the same time, there is increase in the screening effect by both electrons due to extra energy level completely. We need to see this one, completely filled energy level of electrons that are being added. They are completely filled energy levels of electrons being added. And then once I will say screening effect increases by addition of completely filled energy levels of electrons, and nuclear charge increases as a result of additional protons. So down the group, we shall see that the increase in screening effect will always outweigh increase in nuclear charge. I said don't say that the screening effect outweighs nuclear charge. It's the increase. It's the increase in screening effect that outweighs increase in nuclear charge. So we need to see this word whenever you're explaining any periodic term down the group. Outweighs is the increase. You compare the increase. Don't say that the screening effect outweighs nuclear charge. No, it's the increase in the screening effect that outweighs the increase in nuclear charge, leading to a decrease in effective nuclear charge. So when effective nuclear charge decreases, I said, outermost electrons are going to experience less nuclear attraction. So we expect the outermost electron to require significantly lower amounts of energy to be removed. That's a decrease in the first ionization energy. So we are saying from the graphs of ionization energy, one can predict, first of all, you can predict the atomic number of an element by just counting the number of electrons being removed. the other term. Then after putting your graph, you count those dots on your graph. Like if your graph has been plotted like this, if your graph has been plotted like this, so you count these dots you have on your graph. So atomic number, to find the atomic number, we shall just simply count the number of electrons removed, because remember that in an atom, number of electrons is equal to the number of protons. So if you had to count number of electrons here, we shall have 1, 2, 3, 4, 5, 6. So the atomic number here is going to be 6. Let me hope that is very simple to understand. So if you have to look at number 2, we are saying that the number of quantum shells or sub-energy levels. Graphs of ionization energy can help us predict the number of energy shells. Now remember that you've looked at ionization energy. So when you're plotting these graphs, you're going to have a graph in that nature. You're going to have steep curves and areas where your ionization energy is increasing slowly. This is because if you're having an atom like magnesium has 2 electrons outside. So we expect the 2 electrons to be removed. Let me give an example of an element that you can predict well. If 2 electrons are easier removed from the sub-energy level, the ionization energy is going to be quite low. So we shall go to the second inner sub-energy level, removing 8 electrons. So removal of such 8 electrons is going to be significantly requiring lower amount of energy. And if we transit to the next inner sub-energy level that's more stable, we shall require sharp and more energy level. That's why there's an sharp increase in the graph. So the sharp increase in the graph is because we are transiting from the incompletely filled energy level of electrons to the innermost stable, fully filled energy levels, which require higher amounts of energy. Thus, we expect a sharp increase in ionization energy because we have entered the inner stable sub-energy level that's full of electrons. And we say that if something is full of electrons, the energy required to move an electron from it is going to be high. However, after being high, we shall proceed with a gradual slow increase in ionization energy. This is because removal of electrons subsequently from this energy level is going now to require less energy until we reach at the other inner sub-energy level. That will also cause a sharp increase in ionization energy because it's completely filled with electrons and it's inside. So it's thermodynamically stable. Removal of an electron will require significantly high amounts of energy. The graphs of ionization energy can also help us predict the period to which the elements belong. It can also be used to help us to identify the group to which the element belongs. Like the group can be determined by the number of electrons present in the outermost energy level. So if 2 electrons are moved with ease, and you plot your graph like this one, 2 electrons are moved with ease, and then after here we see a sharp increase and then slow increase, sharp increase, slow increase. And if 2 electrons were moved with ease, that means that 2 electrons were present in the outermost energy level. Thus the ionization energy was low. That's why ionization energy was increasing slowly. So that element will have belonged to group 2. The sharp increase was because we have went to the inner sub-energy level completely filled with electrons, and it will require significantly higher amounts of energy. So in this slide, we are going to look at electron affinity. And notice that electron affinity is the same as ionization, is the opposite of ionization energy. So the other side, we are saying that ionization energy is the energy required. Now here, electron affinity is the energy evolved. It's not the energy change. Electron affinity is always the energy evolved. Now, once again, we are saying that if you are using more, make sure that your definition is improved. That's why I was saying energy evolved. I said electron affinity is the opposite of ionization energy. So, electron affinity is the energy evolved when 1 mole of gaseous atoms gains 1 mole of electrons. Whenever you're using more, make sure that everything accompanying it is in plural. 1 mole of gaseous atoms, electrons, ions. So since electron affinity is opposite of ionization energy, instead of energy required, here we say it's the energy evolved. Electron affinity is never an energy change. So this is the energy evolved when 1 mole of gaseous atoms gains 1 mole of electrons to form 1 mole of negatively charged gaseous ions. And this is the equation. So in this equation, we are missing an arrow to show you that electron affinity is about adding an electron to a gaseous atom. And after doing that, we get a negatively charged gaseous ion. That's in terms of plural, but if you want to do in terms of moles, adding 1 mole of gaseous atoms, you get what you add on 1 mole of electrons to form 1 mole of negatively charged gaseous ions. So electron affinity, just like ionization energy, is divided into two. And here we are having the first electron affinity together with the second electron affinity. So as you're hearing, as I explained in ionization energy, first electron affinity, we are going to be adding an electron or 1 mole of electrons to form a uninegatively. Well, what you're interested in is the conclusion part. It's going to be the uninegatively, uni, to show that it's singular, it's one. So you're saying that first electron affinity is the energy evolved when 1 mole of electrons. I said when you're using mole, make sure that everything else is in plural gaseous atoms to form 1 mole gaseous ions. We are very critical about that, and many students lose marks due to that. So first electron affinity is the energy evolved when 1 mole of electrons is added to 1 mole of neutral gaseous atoms. To form what? To form 1 mole of negatively charged gaseous ions. And then here we are saying that note, the gaining of an electron by an atom is entirely an exothermic process. So we don't want to see anything like energy change in your definition. Electron affinity is always the energy evolved. We gave an example, and the example I gave here was with a gaseous atom for oxygen. Now notice that we didn't write oxygen as a molecule. Reason being, we are saying we are using gaseous atoms. We are not using molecules. So the gaseous atom of oxygen, we add an electron to it, it becomes negatively charged. And this is the equation, and it's examinable. This equation carries 1 mark. So we are saying that the first electron affinity of oxygen is negative. Why is this so? This is because the gaseous atom strongly attracts the incoming electron. Now, the more stronger the incoming electron is attracted, the more energy is released. and the more energy is released, we expect the higher the electron affinity. Now you're going to notice that some elements have, some if not many, have their first electronic affinity being exothermic or negative, whereas others have it being endothermic or positive. So why is that the case? Now notice that we have defined electron affinity in terms of energy volt to add an electron. So when you're looking at a neutral gaseous atom, first of all, the explanation is going to remain the same. If effective nuclear charge is high, if nuclear charge outweighs screening effect, effective nuclear charge will increase. Once effective nuclear charge increases, the incoming electron is going to be strongly attracted, and we have said that the more stronger the attraction, the more energy is released, and once more energy is released, we expect a higher electron affinity. Now we are saying that the first electron affinity of oxygen is negative, whereas the second electron affinity of oxygen is positive. Now what I want you to understand, in the second electron affinity, we are adding an electron to already charged ion. So we expect the electrons that they are being added to strongly repel the incoming electron. That means that the electron which is incoming is going to be more strongly repelled than it is attracted by the nucleus. Thus, to add an electron to such a charged gaseous ion is going to require input of energy. So that's the brief explanation about it. So let's see what was written. We are saying that this is because the first added electron in the outermost shell repels the incoming electron. Therefore, energy is supplied in order to overcome the repulsive force so as to add the second electron, making the exchange for the second electron affinity having a sign of positive. Now, this sign of positive is showing that energy is endothermic. And for endothermic things, we saw that they require input of energy. So once the incoming electron is experiencing a stronger repulsion than the attraction from the nucleus, energy is put in so as to add an electron to the ion. So you are saying that, note, the more negative the electron affinity, the more stable the anion is formed. And the examples, we looked at examples for group 7. And you're saying that the chloride ion is the most stable ion, while iodide ion is the least stable among the halides. And why is that the case? The abnormally low value of electron affinity of fluorine atom. Now, this is a common question. Why is fluorine atom having an abnormally low value of electron affinity? It's a very common question. And the reason for that, if you look at fluorine molecule, fluorine has the smallest atomic radius out of all. And since it has the smallest atomic radius, these bonding electrons holding its atoms are going to be strongly repelling each other. Once they are strongly repelling each other due to its small atomic radius, the incoming electron is going to experience less attraction from the nucleus. If the electrons coming, since these electrons are already repelling each other and the incoming electrons also coming, there will be less attraction from the nucleus than the repulsion outside. So the energy that will be evolved will be low. So we are saying that the abnormally low value of first electron affinity of fluorine atom is due to the small atomic size. The incoming electron experiences comparatively strong repulsive forces from the electrons on the nucleus in the fluorine atom. This reduces the overall amount of energy released, thus low value of electron affinity. You can modify that explanation by the explanation I gave you here. Fluorine atom is having its smallest atomic radius. Now in its molecule, fluorine, the bonding electrons are strongly repelling each other. So the repulsive forces exerted here, they also go outside and they affect the incoming electron, so that the incoming electron comes when it's facing a stronger repulsive force than it's being attracted to the nucleus. That means that slightly more energy, but slightly energy is going to be required to add an electron to the fluorine atom. And the second note, we are saying that formation of a divalent ion is endothermic. Thus, an invariant ion is more stable than a divalent ion. We have looked at this in the example of the oxygen atom, the explanation which is above. Now, if you are to start looking at the factors affecting electronic affinity, like as I said, every periodicity element is affected by the same factors. So you find that atomic radius or atomic size, nuclear charge, and then screening effect are going to be the same factors. These factors affect each and every periodic element equally. So you're saying that the smaller, now electron affinity is about addition of an electron to the nucleus. So let's first discuss about atomic radius. If the atomic radius is small, we expect that the incoming electron is going to experience a stronger nuclear attraction than it's being repelled. Therefore, we expect higher amounts of it. The more strongly it gets, the higher the amount of energy is released. And since we measure electron affinity in terms of energy evolved, that means that also electron affinity is going to be high. And if the atomic radius is large or the atomic size is large, the incoming electron is going to experience less nuclear attraction because it's going to be very far away from the nucleus, and is going to experience more of the repulsion by the electrons present in the energy levels. So for the large-sized atoms, we expect electron affinity to be low. The energy being released will be low, and significantly leading to a decrease in the electron affinity. Now notice that when they're telling you to explain electron affinity values, they'll be giving you values in terms of negatives. Let me say negative 217. They give you negative 198 across a group or across a period, whatever. Negative 190. So here we ignore the negatives. Even when you're constructing a graph, you ignore the negatives because the negatives are just showing you that energy is evolved. I hope you studied that in thermochemistry. Electron affinity refers to the energy evolved. So these negatives are showing you the amount of energy being released. You should never consider them. You look at the variables and you state what's happening. If they're telling you to explain the trend, here the trend is going to be electron affinity is decreasing from the specified atom they have given you here to this one. Let me hope you have to note of that. So looking at the second factor, effective nuclear charge, and they say that effective nuclear charge comes after comparing the effect of screening effect and nuclear charge itself. So increase the magnitude of, so if you say that effective nuclear charge exerts its effect onto the outermost energy levels. So you're saying that increase in the magnitude of effective nuclear charge increases the strength of attraction for the electrons to be added. This results into more energy to be raised. Now we say that in earlier videos, effective nuclear charge is having its impact on outermost electrons. So if you think logically, what would happen if effective nuclear charge increases? We say that the outermost electrons are going to be strongly attracted, and similar applies to the incoming electron, because when I was explaining electron affinity, your explanations must be in terms of incoming electron because we're adding electrons. So if effective nuclear charge is high, the incoming electron is going to experience more attraction from the nucleus than it's being repelled. So you expect, and the more it's attracted, the more energy is released, and the higher the value of electron affinity. However, if the effective nuclear charge decreases, that means that the incoming electron is going to be less attracted to the atom, and once it's less attracted, less values of energy are going to be released. Less amount of energy is going to be released. So we expect electron affinity to be correspondingly low. If you look at the next factor, we have in screening effect. So for the case of screening effect, the higher the screening effect, the lower. Now screening effect is as I explained earlier, is the force that is being exerted by electrons onto the outermost electrons. Now here is going to be these electrons on the outermost energy level onto these incoming electrons. So the screening effect is what we call this one. And we say screen effect increases with increase in the number of energy levels. So we are saying that the higher the screen effect, the lower the electron affinity will be. Since we are measuring electron affinity in terms of energy released, we shall be saying that this is because the incoming electron will be experiencing more repulsion, e.t.c. And once it's less, the incoming electron is less attracted by the nucleus, significantly low amounts of energy are going to be released. And since low amounts of energy are going to be released, we expect also the electron affinity to be significantly low. That's why we shall be having low values of electron affinity. Just a reminder, when you are given trends to explain in terms of electron affinity, values are going to be negative. This is just to show you that this is energy evolved, energy being evolved, but negatives shouldn't be applied anywhere. When you're drawing graphs, you should eliminate negatives. You should only consider values. So in proceeding, we are having explanation of electronic configuration. Like as I told you, electronic configuration, you're always looking at either the atom is having a half-fully filled or fully filled sub-energy level. And we are saying that those ones are, you can either use thermodynamically stable or energetically stable. So in terms of electron affinity, we are looking at electron gain. In ionization energy, we are looking at removal of an electron. So what's going to change here, the conclusion is going to change in terms of gaining electrons. So you're saying that atoms of elements with either half-full or completely filled sub-energy levels are energetically stable and therefore do not easily gain electrons. As such, heat energy must be supplied in order for the electrons to be added. This reduces the magnitude of electron affinity, making the value. This must be supplied in order for the electrons to be added. This reduces the magnitude of electron affinity, making the value obtained to be less than expected. Now, once we are having a fully filled or fully filled sub-energy level, we expect it to be energetically stable. If you fear using this word, you can use thermodynamically stable. They all mean the same thing. So once it's thermodynamically stable or energetically stable, what happens? Addition of an electron to this atom is going to be more difficult. Therefore, less energy is going to be released. And once less energy is released, the value of electron affinity will be low. Now we are seeing that for the atoms of elements whose sub-energy levels attain a stable electronic configuration, when they gain electrons, release a lot of energy, resulting into high electron affinity. And here we are looking at the atoms with neither halfly filled or fully filled sub-energy levels, like having one electron, having 4 electrons, like that, depending on the sub-energy level you are dealing with. So let's proceed by looking at the variation of first electron affinity across the period. Now we shall begin with the general trend. Like I told you, these questions are said to first state the trend and then you explain. This is how you are supposed to bring your answer up. We expect you to be organized. Now the general trend across the period. Now what happens across the period? There's an increase in electron affinity from sodium to chlorine. And why is that the case? First brainstorm in yourself. Before reading explanations, you first brainstorm in yourself and you ask yourself, why is electron affinity increasing across the period? What happens across the period? So you find that across the period you're having a decrease in atomic radius. So we expect the incoming electron to be strongly attracted progressively across the period. So the explanation for periodicity is going to remain the same state. We shall talk about nuclear charge. We shall be talking about screening effect, and after talking about that, we talk about what outweighs each other, and we talk about effective nuclear charge, and then we talk about atomic radius. So explanation, nuclear charge increases. Why it causes an increase in nuclear charge? Because due to addition of a proton to the nucleus. Screening effect remains almost constant. Why is that the case? This is because an electron is being added to the same existing energy level. So you see in the marking terms, you state that effective nuclear charge increases, and then you give us the reason for it increasing. You say that the screening effect remains almost constant. There's half a mark there. You also give the reason why it's doing that way. That's how we mark chemistry. You state the variable term you are doing, the effect on it, and you also state the reason why it's that way. The screen effect remains the same since electrons being added to the same existing energy level as one moves from sodium to chlorine. Now we are saying that there is therefore a decrease in atomic size from sodium to chlorine due to an increase in effective nuclear charge. And you're saying that the effective nuclear charge is increasing, reason because screening effect is remaining almost constant. So nuclear charge increases and outweighs the increase in screening effect. And once increase in nuclear charge outweighs increase in screening effect, effective nuclear charge also increases. That means that the incoming electron is going to experience a stronger attraction, and once the strong attraction, more energy is released. And once more energy is released, that means that we also expect a higher value of electron affinity. So you can write down the notes, or you can pause the video, you review the notes for the explanation to sink. Now here we are going to start exceptions. Now exceptions for electron affinity are going to be explained the same way like for ionization energy. So I'm only going to explain 2 examples. What's going to vary is the conclusion. So they're telling us that the electron affinity of magnesium is more positive than expected. Why do you think that's the case? It all lies in electronic configuration. If you look at the electronic configuration of magnesium, the 3s sub-energy level, which is the outermost, is completely filled with electrons. And if it's completely filled, we expect it to be thermodynamically or energetically stable. So that being the case, that means that the incoming electron is going to be less attractive. Thus, energy is going to be required to add an electron to such an atom that is thermodynamically stable. So since we are supplying energy, the electron affinity is instead of energy being released, we are going to supply energy. That means that the electron affinity is going to become positive, or it's going to be endothermic, because this atom is thermodynamically stable due to having a completely filled 3s sub-energy level. Since it's completely filled and thermodynamically or energetically stable, energy must be put in to add an electron to such an atom. That's why we shall find the value of electron affinity being positive or endothermic. Now similarly, the first electron affinity of phosphorus is less negative than that of silicon. And here, when you are comparing two atoms, I've already mentioned this, you should write down their electronic configurations first. So here you start by getting a mark when I'm marking. So you see that phosphorus is having a half-Li filled 3p sub-energy level. So you are seeing that phosphorus has a 3p sub-energy level, which is half full of electrons. And since it's half full of electrons, that means that it is thermodynamically or energetically stable. Thus, addition of an electron will require some resistance. So therefore, to add an electron such atoms that are energetically stable, we need to supply energy. And once energy is supplied in, the electron affinity, instead of being negative to show that energy is being evolved, it will be positive. So we shall expect the electron affinity for phosphorus to be less negative than that of silicon, because silicon has a neither completely filled or halfly filled sub-energy level, 3p sub-energy level, which is thermodynamically or energetically unstable. Therefore, addition of an electron will require the incoming electron therefore will be more strongly attracted than it's being repelled. More energy is going to be released, leading to a higher value of electron affinity. Now let's look at variation of first electron affinity down the group. Now, what happens down the group? That's the first thing you should ask yourself. Now here I didn't specify in my notes, but you should specify. Like here in my notes, I give an example of group 7. I don't know whether you have seen that, but I didn't state it. So for the people writing, make sure that you say that, for example, group 7. So you're going to be explaining why is electron affinity decreasing from group 7. So what happens down the group? That's the first thing you should ask yourself. So if you see down the group, we shall be having an increase in atomic radius. And as you're increasing atomic radius, as I already explained earlier, the incoming electron will be experiencing progressively lower and lower nuclear attraction. And once it's less attracted, that means that subsequently energy being released is going to decrease, causing a decrease in electron affinity. However, fluorine is going to have an abnormally low value of electron affinity, and I told you this is a common question. We usually ask it. I explained it earlier on. I'm going to pardon one more time before we look at the explanation. I told you if you look at the fluorine molecule, fluorine is having its smallest atomic radius. The fluorine molecule is held by this bond, and this bond is short. So these are bonding electrons. These bonding electrons are going to repelling each other. So in the fluorine molecule, we already have some repulsive forces which are greater. So if we are bringing in another electron here, yet we already have these electrons in chaos, already repelling each other, that means that energy is going to be supplied to add an electron on this fluorine atom. That's the reason why it's having a very low value of first electron affinity, because of its smallest atomic radius. The bonding electrons are strongly repelling each other. So let's start looking at the explanations. First of all, the trend is first reaction affinity decreases generally down the group from chlorine to bromine. However, fluorine shows abnormally low value of first electron affinity. Explanation. The explanations for periodicity remain the same. We talk about nuclear charge and its effect. Both nuclear charge and spin effect increases down the group. Nuclear charge is increasing because we are adding electron, but spin effect is increasing because we are adding a completely fully filled energy level of electron. And after talking about those two, we talk about what one outweighs each other, and we already saw that down the group, increase in spin effect will always outweigh increase in nuclear charge, causing an increase in atomic radius down the group. So, as such, electronegativity of the atoms decreases down the group, and therefore the incoming electron becomes less strongly attracted towards the nucleus. The more it's less strongly attracted towards the nucleus, the less the amount of energy being released, causing a decrease in electron affinity down the group. However, the electron affinity of fluorine is abnormally low, and here we are saying the reason for that is due to its small atomic size or atomic radius. The incoming electron experiences strong repulsive forces from the electrons around the nucleus in the fluorine atom. This reduces the amount of heat released, thus low first electron affinity value for fluorine. Now I want you to remember that chemistry is about presenting. Now looking on to the next term, we shall see electronegativity. Now, electronegativity, this is not an energy change. The only energy changes we are having electron affinity and ionization energy. So note that electronegativity is not an energy change. When you are considering electronegativity, it's just a tendency. Similarly applies to electropositivity. So the opposite of electronegativity is electropositivity. So we are saying that electronegativity refers to the measure of the tendency of an atom in a covalent bond situation to attract bonding electrons toward itself. As we are hearing the name, electronegativity, the ability of an atom in a covalent bond to attract bonding electrons towards itself. So electronegativity only applies for non-metals. Electronegativity only applies for non-metals because they are those ones that engage in covalent bonding. Like for the examples we gave, oxygen, hydrogen, and chlorine, and then we said e.t.c. Then we talked about the factors that affect electronegativity. Now these factors for periodicity are going to remain the same. Nuclear charge, screening effect, and atomic radius. These factors are always remaining the same and apply everywhere for as long as the factor you are being looked at is in periodicity. Now we are going to start explaining each of the factors listed one by one. Now as I've already repeated this over and over again, I hope everyone now understands what effective nuclear charge means and which impact does it have on the electrons. The smaller the effective nuclear charge, the lower will be the electronegativity. Why do you think that's the case before even reading through this? Electronegativity is the tendency for the atom in a covalent bonding situation to attract bonding electrons towards itself. So the low effective nuclear charge, the bonding electrons experience a lower nuclear attraction by the atoms in this covalent bonding situation. That means that we expect a low electronegativity value. And we say the electronegativity is not an energy. This is just a tendency, similar to electropositivity. They are just tendencies. In periodicity, the only energy values that we're having is ionization energy and electron affinity. Other than that, don't think about anything like energy change. Electronegativity is a tendency. Similar applies to electropositivity. So, we're trying to reason out this. If effective nuclear charge is high, we expect the bonding atom in a covalent bonding situation to attract strongly the bonding electrons toward itself. Like if you look at hydrogen fluoride, there is a bond here. So since fluorine is having a smallest atomic radius, we expect it to have a very high effective nuclear charge. That means that it's going to attract strongly these bonding electrons towards itself compared to anything else like hydrogen bromide. That's if you are to consider down the group. Let me hope that has been understood. So proceeding, we are saying that if effective nuclear charge is high, bonding electrons experience a stronger nuclear attraction by the atom in the covalent bonding situation. Thus, electronegativity is going to be high. So we shall proceed into the next element, which is atomic radius. Now this one is clear. The smaller atomic radius is electronegativity is about pulling bonding electrons towards the atom. That means that for the electronegativity to be high, we need a smaller atomic radius. And if electronegativity is going to be low, that means that it was a bigger atomic radius. That's why we are saying the smaller the atomic radius, the higher will be the value of electronegativity. For a smaller atomic radius, the bonding electrons experience a greater nuclear attraction because they are nearer to the nucleus, leading to a high electronegativity value. The larger the atomic radii, the smaller will be the electronegativity. Now looking onto this, we shall also have a screening effect. Now these ones are going to remain the same, so I'm going to skip this one for a moment. Let's go straight away to variation of electronegativity across a period. Now as I told you, and I'm repeating these, questions will always come in such a way that state and explain a trend. You are supposed to first start by stating the trend, and then you go to explaining the trend. Be conscious and aware about that. So you're saying that the trend, electronegativity will be increasing, like this is a period 3. For people writing, make sure that you say that, for example, period 3. So we are saying that electronegativity increases from sodium to chlorine across the period. And the explanation for this, first figure out in your head, why is it increasing across the period? Look at the things happening across the period. Across the period is where we are having a decrease in atomic radius. And why is that happening? That means that effective nuclear charge is also increasing. And across the period, you'll find that screening effect will remain almost constant. And since electronegativity is the tendency of pulling electrons towards the atom, that means that moving from left to right across the period, nuclear charge is increasing. And why is it increasing? It's due to additional potential nucleus. Screening effect remains almost the same. And why is it remaining almost the same? Because electrons are being added to the same energy level. So what happens? Increasing nuclear charge outweighs increasing screening effect. So you'll find that effective nuclear charge will increase, leading to increase in the nuclear attraction for the bonding electrons. Now we are talking about bonding electrons because electronegativity only applies for atoms in a covalently bonding situation. That's why we talk about bonding electrons, as I illustrated, hence increasing electronegativity. Now in this video, let's look at variation of electronegativity down a group. Like here we gave an example of group 7 elements. So if you pause the video, take notes, have your periodic table look at group 7. So as I told you before explaining variations, you say the trend. after stating the trend, you give your explanation. If you miss out stating trend, just know that you won't be awarded any mark for the explanation. Everything will be null. So we are looking, well, I told you before explaining something, first question yourself, what's happening down the group? So you find that down the group, you always have an increase in atomic radius. And since you're having an increase in atomic radius, that means that the tendency to attract electrons is going to be progressively decreasing. That's why we are saying down the group, both nuclear charge and spin effect increase, but increase in spin effect outweighs that due to nuclear charge, because an extra shell added as one moves from one element to the next is being added. Therefore, effective nuclear charge decreases. And if effective nuclear charge decreases, we looked at the factors affecting electronegativity. We gave three. We talked about effective nuclear charge, we talked about swinging effect, and we talked about atomic radius. The smaller the atomic radius, the higher the value of electronegativity. And the larger the atomic radius, the less the value of electronegativity. The higher the effective nuclear charge, the higher the value of electronegativity. And the lower the effective nuclear charge, the lower the value of electronegativity. And here we told you when you're explaining electronegativity, we are always talking about bonding electrons. So make sure that you don't miss it out in your work. Proceeding to the next element, we are going to look at periodicity of electropositivity. Now, electropositivity, the most acceptable definition refers to the tendency of an atom to lose its valence electrons. That's the authentic definition of periodicity. If you're writing, say get a paper and summarize it somewhere. Electropositivity refers to the tendency of an atom to lose its valence electrons, and that atom must be for a metal element. So electronegativity is for atoms of nonmetals, and electropositivity is for atoms of metals. I gave two definitions, and so if you are to look at explanations of electropositivity across the period, we shall explain things in the same way. Now you see things are repeating. We are talking about effective nuclear charge, we are talking about screening effect, we are talking about nuclear charge, we are talking about screening effect. Now these are some of the key items that shouldn't miss in your explanations. And we are seeing that across the period, effective nuclear charge. Now let's first pause the video and talk about something. We have defined electropositivity as tendency to lose valence electrons. What do you think is going to affect the loss of valence electrons? That means that the valence electrons or atmos electrons are going to be easily lost when atomic radius is larger or when the effective nuclear charge is low. Remember, effective nuclear charge is the one that attracts the outermost electrons. So if effective nuclear charge is low, outermost electrons are going to be less attracted to the nucleus. That means that there will be more ease in losing them. And if screening effect is high, that means that electrons are having a stronger repulsive force between themselves, which will lead to easy loss of electrons. So you are saying that electrons present in the atoms become more strongly attracted to the nucleus as one moves across the period. Now across the period, what's happening? Across the period, screening effect is remaining almost constant because you're adding an electron to the same energy level, but nuclear charge is increasing because due to increasing the number of protons in the nucleus of the atom. So we expect effective nuclear charge to increase across the period. And across the since effective nuclear charge is increasing across the period, outermost electrons are going to experience stronger nuclear attraction. That means that the tendency to lose those electrons is going to be progressively decreasing across the period, which is leading to a decrease in electropositivity across the period. So when you're summarizing, notice that we explain electropositivity in terms of ease of loss of electrons. So you have to look at the factors that will cause the ease of loss of electrons. So let's look at variation of electropositivity down the group. So you're saying that electropositivity increases down the group. So variation of electropositivity down a group. Electropositivity increases down a group in the periodic table. What would be the most significant explanation? So we shall say that down the group there is increase in nuclear charge and screening effect. Now, for every I eliminated giving explanations for the increase in nuclear charge, but when answering questions, for every change that you give, you have to give a reason for it. Like you said that there is increase in nuclear charge. Why is it increasing? Due to addition of protons to the nucleus. And why is screening effect increasing? Screening effect is increasing due to addition of competitive field energy level of electrons down the group. Now here they are saying, after talking about that, you talk about what outweighs each other, and you have been explaining everything down the group, and you have been saying that screening effect is always outweighing nuclear increase in screening effect has been always outweighing increase in nuclear charge. And what happens if increase in screening effect outweighs increase in nuclear charge? You'll find that effective nuclear charge will decrease. And once effective nuclear charge decreases, that means that the outermost electrons are going to be less attracted to the nucleus. That means that the tendency to lose electrons is going to be high. So we expect electropositivity to be increasing down the group, because electropositivity is the measure of the tendency with ease by which electrons are being lost from an atom. So that's it for electropositivity across the group. So in this slide, we are going to look at the factors affecting electropositivity. And here we are having effective nuclear charge, screening effect, atomic radius, and electronic configuration. So I've already explained effective nuclear charge, I've already explained screening effect, I've already explained atomic radius. Let me explain electronic configuration. So electropositivity is low when the outermost sub-energy level is either half-filled or fully filled with electrons. And I've already explained that that's due to its thermodynamic stability or energetic stability. Therefore, the tendency to lose an electron is going to be low. Atomic radius, the smaller the atomic radius, the stronger the outermost electrons are, the valence electrons are going to be attracted to the nucleus. That means that if atomic radius is smaller, electropositivity is lower. But if atomic radius is larger, electropositivity is higher. Because if atomic radius is higher, outermost electrons are less attracted to the nucleus. That means that the tendency to lose such electrons is going to be very high. If you look at screening effect, electropositivity is going to increase with increase in screening effect, since outermost electrons will be more strongly attracted than the more strongly repelled than they are attracted by the nucleus. So we expect that screening effect, increase in screening effect will increase electropositivity. And similar applies to nuclear charge. The decrease in effective nuclear charge will lead to a decrease in attraction of the outermost electrons towards the nucleus. That means that they will easily be given off, or they will easily be lost. So as we are concluding, we are going to be looking at one of the last points of periodicity. and in this case you are going to be looking at melting point. Now melting point refers to, as we covered in your level, what you want to see when you're defining this. You want to see, you're talking about that it's a constant temperature. It's a constant temperature at which a pure solid transits to liquid, provided standard conditions like standard pressure is provided. Now, what are the factors affecting the magnitude of boiling or melting points? Now, when you're explaining these two terms, boiling or melting points, you explain them the same way. In metals, we look at number of electrons contributed per atom during metallic bond. Like if you look at aluminium and you look at magnesium, you look at the outermost energy, you look at the outermost configurations. Now, in this case, we are going to be using O level. If you look at that for magnesium to end with 8.2, if you look at for aluminium, it's going to end with 8.3. So that means that aluminium is going to provide 3 electrons for metallic bonding, whereas magnesium is going to provide 2 electrons for metallic bonding. So we expect the metallic bond for aluminium to be stronger than magnesium, because aluminium is providing 3 electrons for metallic bonding, whereas magnesium is providing 2 electrons for metallic bonding. But note that this only applies for metals. So strength of metallic bonds, we look at number of electrons contributed per atom. Aluminium will contribute 3 electrons since it has only 3 electrons available in its outermost energy level. Thus, we expect it to form stronger metallic bonds that had to break. Thus, boiling and melting points for it are going to be higher. Whereas in magnesium, it has 2 electrons in the outermost sub-energy level. That means that the metallic bonds are going to be relatively weaker. We expect melting point and boiling point in aluminium thus to be greater than that in magnesium. So you can look through the notes as I stated them and to write down what's being required. So next factor we are going to look at atomic radius. How does atomic radius influence the nature of melting point? Now atomic radius will help us with the effect of bond length. Bond length is a very crucial element when you're explaining melting points. It's applied everywhere. So the smaller the atomic radius, the shorter the bond length, and the shorter the bond length, the more stronger it becomes. The longer the bond length, or the larger the atomic radius, the longer the bond length, and the longer the bond length, the more weaker it becomes. Now I want you to understand that you should compare this one to a normal life situation. If you have a thread, the shorter the thread, the more stronger it is, and the longer the thread, the more weaker it is. Similar applies to here with atomic radius. That's why we are saying that for atoms with small atomic radii, their bonding electrons are strongly attracted to the nucleus, making the interatomic distance shorter. And once it's shorter, it will make it stronger. The explanation here might be more complex, but try to summarize what I'm giving you. That if the atomic radius is smaller, there will be shorter bond length between the individual atoms. That means that if the bond is shorter, it will be stronger. And that means that more energy will be required to break such bonds. Thus, for shorter bonds, there will be a higher melting or boiling point. And then, if the atomic radius is larger, we expect the bond length to be larger too. So the longer the bond, the more weaker it becomes. That means that the less will be the melting or boiling points. Now, as we have come to an end, we are saying that what are the factors affecting magnitude of melting points of non-metallic elements, like the ones that I gave in the previous video in the previous slide were for strictly metals. So non-metals, what affects melting points in non-metals? So non-metals, we shall be looking at molecular mass. This is a common concept. Molecular mass, especially, for example, in group 7, number of electrons used for covalent bonding. Now this one won't be tackled much, but in non-metals, but it can be applied for some few elements. Then lastly, we shall be looking at number of atoms which are covalently bonded together. We shall look this more in depth with group 4 elements. So notice that each of these ones will be looking depth in when you're handling individual topics in inorganic chemistry. So that marks the end of our video. This has been Welcome So you can reach me out on the following contacts for more details and for explanations in case you didn't understand anything. Have a good and I wish you success in exams for those ones in senior 6, and for those in senior 5, keep going.